And then we will have the announcement of EICS 2023, which will be done by José Camps from University of Minho on behalf of the steering committee of EICS. So for now, we start with the keynote, as I said, from Steve Brewster. So Steve Brewster is a professor in human-computer interaction at the School of Computing Science at the University of Glasgow. And he's the head of the multimodal interaction group there. So Steve has been around for many years. Started, I was trying to find only positive things to say. So that's true. So he started by doing a PhD on auditory user interfaces, and then he's been working on multiple modalities, one by one or integrated together. He did many of things which were innovative, like the organization of the first or second or several of the first mobile HCI conferences, for instance, in Glasgow and in other places. So in Glasgow and different universities in Glasgow. He's been working on different ways of interacting, and globally he has been working for all the time on the sensory motoric loop of human interaction, combining modalities all together, bringing innovative technology and innovative design all together to build a interface that will increase the bandwidth between users and computers. Beyond that, Steve has
wrong person.
The guy conference in Glasgow. That was a huge achievement because the UK has never had hosted this conference, and it was one of the big key elements to bring Kai to Britain. So that was it. And then, of course, he's part of the steering committee of Kai for many years now. So I think that I've said enough. Maybe one thing, and I guess you will talk about it, is owner of the ERC Advanced Grant, Viajero, on new technologies for saving the time of people when they are using transportation. So this is it. Please welcome Steve and
Thank you, Phil. Actually, so one thing, I'm going to stop this first, and then I'm going to use subtitles. And then we'll start again. Hopefully you can see some words as I speak them as well. So Phil mentioned this Viajero project, my ERC Advanced Grant, which is that's the thing I'm going to talk about today. And that's all about passengers. Actually, it's a super fun project. We're having such great fun doing all the things on this project. It's one of the most favourite projects I've had in my career, I think. So the aim of the project is all about improving passenger journeys, and we're doing that by using immersive, virtual and augmented reality. And really we're looking at how we can help people just use that travel time in a more interesting way, be entertained, work, collaborate, do interesting things. So let's first of all take a step back in time. There we are. That's what the future looked like in the 1950s. So people are driving along this road into this futuristic looking city in the background there. The front seats of the car, of course, they've rotated around. People look like maybe having a cocktail or something on a little table. There's some kind of TV screen between them. So they're having a kind of nice social experience. Has that materialized? Well, so this is commonly what you might see in a concept car. This one was from a company called Rimac, and somewhat similar. So you can see the front seats have rotated around, so that the guy in the front can talk to the guy in the back. Not quite sure what they're doing on that table, but maybe they're playing some kind of game or something like that. So still a concept right now. You can't really buy a car like that, but the concept is still there even after all that time. But what's the reality? Maybe the reality is a bit more like that. Certainly was when my kids were a bit younger. You were squished into the back seat of the car, and people shouting and arguing and all sorts of things going on. So, it wasn't quite the serene experience that we saw from the 1950s there. So what we're thinking about, we're trying to support new passenger experiences, maybe to escape from the situation the lady was in the last photo to do something else. And we're trying to do that through extended reality, so a combination of virtual and augmented reality. And one particular focus of ours is on automated vehicles. So in the future, if the vehicles are automated, you're not driving, well, you're a passenger. So there's passengers now, there'll be more passengers in the future. What might you do? Yeah, as I said before, we're looking at things like entertainment, productivity and collaboration. So how could you do interesting things whilst you're traveling? That might be your short commute to work, or it might be your international flight somewhere else. And to make things that support interactivity, to support entertainment, productivity and collaboration, there are three kind of big challenges that need to be solved. The first one is around interaction. The second one is about sensing, and the third one is about motion sickness. So I'm going to go through these throughout the talk. So if you think about being a passenger now, well, actually in Europe we spend about 12,000 kilometers a year on public and private transport. So we spend a lot of distance and time traveling. That might be buses, planes, trains, in the future maybe autonomous vehicles. And actually, yeah, if you think about it, in a regular vehicle, and you're the driver, at least you've got something to do, you're driving. But in the future, if you're not driving, then what are you going to do? You're just a passenger. So what might you do? And typically you have kind of a limited access to technology in that scenario. Maybe you've got your phone. If you're on the bus, you might use your phone, or in the back of the car, you might use your phone. Maybe a tablet, maybe a laptop on a longer type of activity, you know, like a plane or a train. Maybe there's some kind of seat back display. But all those devices are much smaller and less powerful than the ones, for example, you might have in the office, or you might have a big TV at home. So you're limited by the technology. So our aim is to radically improve journeys using extended reality and unlock this potential of traveling time. So it's not just wasted, you can actually use it for something interesting. So benefits. Well, if I'm using virtual reality, for example, I could completely replace the environment I'm in. So maybe that lady who was squished between the two kids, she could think she was in outer space, or underwater, or by the beach. You know, we could present to her a completely different display in virtual reality. Augmented reality, at least I could augment the environment around me. If I can't see a window, I could just draw a window and I could see through it in augmented reality. I could appropriate elements of reality into my experience. So maybe I might use the seat back in front of me for haptic feedback, or the armrest or something like that. Or I might use other things in the environment. Maybe I might augment other vehicles around me on the road as parts of a game, parts of an augmented reality game I could be playing. And then maybe I can sense the motion of the vehicle I'm in, and I could use that in my experience. You know, for example, maybe I could make my 30-kilometer-an-hour drive feel like 60, or feel like 150. So I can make my journey feel more exciting by changing my experience of it. So as I mentioned, we're thinking about three kind of broad topics. And we'll talk a bit about these, and then we'll go and think about what are the challenges we need to do to make these come true. So the first one is entertainment. Of course, we consume a lot of media already whilst we're traveling, but maybe I want an IMAX cinema. You know, that's the huge wall-sized cinema. Maybe I want to be attending an IMAX cinema while I'm in the back of the car. Maybe I want to be playing an immersive game. And these are great, but there's a lot of issues that come up with this idea of this head-locked content, where the content is in front of me, but the vehicle might be moving. And that's what can cause motion sickness, which we'll come back to a lot later on. So here's an example. So this one isn't driving, this one is in the office, but what you can see there, bottom right, is Mark is sat at his desk, he's wearing a VR headset, he's looking at cinema. So he's in a virtual reality cinema. Fiona's there as well. He can see the cutout of Fiona captured by a depth cam, rendered in his scene. She can see the equivalent of him as well. So they're kind of sharing the cinema experience, even though neither of them is in a cinema and neither of them are co-located. So you could imagine that one of them could be in a car, one of them could be elsewhere, and they can share this cinema experience and be entertained by this large screen when they're traveling. Sounds quite nice. Here's another one. So this is you're playing some kind of space game, space shooting game whilst driving around. I'll explain a little bit more about this later on. You can see Mark there shooting some spaceships as he's driving around in his vehicle. And the movement of the vehicle in this case is mapped to the movement of his spaceship in space. This is part of the reason why the project is so fun, because we get to drive around playing games and we get to call that work. So entertainment. Maybe we do have to do some work sometimes. Well, in my office, you might have, got two nice a big multi-monitor setup in your office, which is great. It can have lots of windows open. But when I come to traveling, that's my phone. So that's not quite so convenient. Maybe I could have my multi-monitor setup out and about when I'm on the move. So here we go. Here's another project where we were looking at how you might lay out a workspace using virtual reality. So here you've got screens all around you. We were looking at how you would lay those out, how you might support interacting with such large screens, because if you're not careful, there's a lot of neck rotation and that hurts. We were looking at how to bring the keyboard in. This was a project with Logitech. So this was a prototype at the time, but they now have a keyboard which you can bring into a VR scene. As yet, we haven't done a very good job on input in VR. So the keyboard is still the best. So bring that into the VR scene, track my fingers, then I can do good typing. And that's actually quite hard to do, because registering those devices in your fingers very, very precisely is what you need in order to be able to do good touch typing in VR. So you can imagine then in the back of your car, you have your multi-monitor setup. So here we go, look, we've got 3 windows open. And of course, the interesting thing about these are stabilized to your view. So when I turn right, all the screens don't go over here, because that's not very, very much use. In the space game, that was fine, because that was just driving your ship through space. But in this case, I need them stabilized, otherwise I can't work on my document if it's behind me, because I've turned on the road. And then the other area is collaboration. So what we don't want to do is put people into VR and have them cut off from the world and their friends and everything else. So we're trying to think about how you could allow people to work together or do things together. That could either be 2 people in the car, or it could be somebody in the car and somebody elsewhere. So here's me and Katrina. We're in the back of the car, and we're doing a kind of a tour bus ride around Glasgow. Just in the back of Katrina's view there, you can see Central Station, which is a kind of big old Victorian station in Glasgow. And as we drive past that, we get some information overlaid on it, on the virtual model, and you can see that we're both co-located in the same VR scene. We'll see a little bit more about this later on. But we can see avatars of each other, we can see each other's hands, we can talk to each other. Well, here's another version. This is the space game, but actually now we can play together in the back of the car on a very rainy day in Glasgow. So, lots of great scenarios, but it's not quite as easy as that. There are some things that we need to think about in order to be able to make those scenarios really work. And that's what we're working on throughout my VR Hero project. Some steps have been made, but there's still quite a long way to go on some of these. So, research challenges are based around these 3 things I mentioned earlier on. Interaction. So, you're squished into a small space. You've maybe got a seatbelt on strapping you in. So, interaction is a bit different to how it might be on the desktop. But we need to support high bandwidth, 3D spatial interactions, but we've got to do them in a small space. I can't be punching the person next to me because I'm trying to do the kind of typical interactions you might have in VR. And I need to think about the physical and social environment. So if I'm sat next to somebody if I'm sat in the middle seat of an economy plane flight, I really need to know what the people around me are, so that I don't hit them, or if they want to get past me. So when you start to use this technology in public settings, interesting issues start to turn up. Then there's a lot of issues about sensing. Now, of course, latency is a big issue with VR headsets. Using a VR headset in a car also causes problems with motion sickness if your sensing is not fast. But for example, what you really need to be able to do, and we'll come back to that in a lot more detail, is how to separate my head movement from the movement of the car. Most VR headsets, if they have an IMU or something, it doesn't know whether it's me moving or the car moving, and that can be really problematic for creating those headlock displays I just showed. And then the kind of elephant in the room is motion sickness. So there's all these great things I could offer you, but if you get sick using them, then no one's going to want them. So we have to think about how we manage motion sickness in these scenarios. You know, people get motion sickness right now reading books in cars, and that's going to be potentially worse if you're using VR. And this headlock content, where you know the car's turning, but the cinema display is still in front of me, that's the kind of thing that causes most of the problems. So we'll talk about these in turn. First one, interaction. Yeah, the big problem here is this confined space. I haven't got all that room I might have if I'm doing VR at home, you know, in my living room, where I can walk around, I can do big movements. You just can't do that. So, for example, how then might I map smaller movements into a larger space? How might I apply movement gain, for example, to be able to reach that object which is a bit further away? How can we make efficient, high throughput interactions? That's a really hard one. Nobody's really done very well yet in VR. And all we did is we just brought the keyboard in, which you could say, well, that's cheating, but it's something. And also then the thing we've been thinking most about just recently is how can we use the physical environment to help us? So rather than being an obstacle, you could think, well, maybe the real world environment could be of help. So what we've been doing, we're in the middle of a series of experiments actually, is looking at how we might use physical surfaces around you to give passive haptic feedback. So in this case, Daniel is touching on the plane seat in front of him. So if you imagine that you put your virtual object precisely aligned with that seat back in front of you, when I touch the virtual object, I'm touching the seat back, and I get fantastic haptic feedback because I've got a solid seat which I can perceive as part of the object that I'm touching. So the passive haptics can be really strong. But of course you have to be able to detect the surface of the seat and detect the finger very precisely to be able to do that. You might create things in different ways. Here we were using the green area as a kind of big touchpad, and then he's got a display in front of him. Or you might, for example, use a VR headset to kind of see things on the tray table. The nice thing about the tray table is it's got that slidery thing in the top, which I know where you're meant to put a pen or something, and there's a nice dial where the cup's meant to go. So you've got some physical features that you can nicely take advantage of. Oh, of course, there's the armrest as well. You know, you might use the armrest to do different things. So lots of interaction possibilities there, and we'll be looking at how you might design to, for example, use that seat back to give you the passive haptics, and it actually works really well, much better than in air tapping on objects where you get no feedback. That's kind of quite poor performance. But the thing that comes up a lot when you start thinking about this is those interactions have got to take place in a social setting. I could be surrounded by people I know or people I don't know. And there are things that I would do in those scenarios and things that I wouldn't do in those scenarios because I might look stupid. So we've been thinking a lot about this idea of social acceptability. Interesting things come up about where should you put the displays. You know, if you have an AR display, you can put it anywhere. But where do people actually want to put them? What kinds of interactions are socially acceptable? I can do all kinds of different things. But what things are acceptable? I'm not going to talk so much about that in this talk, but also we've been thinking about, well, what information do I need then from the real world in my augmented world to make sure I know what's kind of going on around me, that I can understand the physical space and what's happening. So first of all, display layouts. So we've done a couple of studies on this now, looking at how people want to lay out content in different kind of scenarios, working scenarios, entertainment scenarios, in different types of transport. So this one here, it's kind of a taxi type scenario. So the driver's in front, you're in the back seat. So what we got people to do was we got them different numbers of displays and said, okay, well, how would you like to lay out these kind of displays in this scenario? It's thinking a bit more, actually this is a kind of interesting simulation of augmented reality. but in virtual reality, which we do quite a lot because most of the augmented reality headsets are not that good yet, certainly not as good as the virtual reality ones. So what you find is that people really use the physical constraints of the environment, like the seat back in front. They really wanted to put things on the seat back. You can put them anywhere they like. This is all virtual reality. But actually, people really like to put them on the seat back, so that they were kind of aligned to those physical surfaces. Here's another one on a plane. It's a little bit distorted in its kind of perspective because this is taken from the headset. In this case, you've got a couple of avatars sat next to you, moving around, doing things. And we asked people, well, how would you want to lay out your displays? Initially we thought, okay, well, people just lay them out horizontally. They'll make like what I have in my office. I've got my displays laid out like this. Now, people didn't want that because the trouble is, the display on this side means I'm looking at that guy right next to me, and that feels weird. People didn't want to be staring at the guy next to them for long periods of time. So actually, what people chose was a vertical stack of screens, which is not what we'd initially thought. It makes perfect sense, but it's not what we'd initially thought. So it's not like the office. People wanted that vertical orientation of screens so that they didn't have to have these weird social interactions with their neighbours. This is a train, so a typical train scenario with a table between you and some people sitting opposite you. So again, you can put the screens wherever you like. But actually what we found was that people put them a lot on the table, just where you might put a magazine, a book, or your laptop right now. What people didn't really want to do was put them directly in front of them. You could say, well, why not? I'll just have it in front of me. That's a really convenient location for a movie. But the trouble with that is that then I'm staring right into the eyes of the person opposite me, and they're looking back thinking, why is that guy staring at me for 5 hours? So the social situation there really forced people to think, well, I don't really want to do that. That's weird. So they ended up putting them on the tabletop because that's a kind of more familiar scenario. Same kind of thing in the subway. If I don't know how it is for you, but if you're on the subway in London in the UK, you do your very best not to ever look at anyone in the face. You're looking here, down here. So I could put a screen right in front of me, but then I'm staring at someone in the face. And of course on the subway, they put all the adverts up here, so you have permission to look up here, out of the way. They don't put things right in the eye line. And we completely found that. People didn't want to put displays over people's faces. They put them in other locations. So the interesting thing there is, augmented reality gives you options to do anything, but there are some constraints from social and real things that mean you don't put them in every place. There are actually some limitations. So that's the kind of display side. What about the input side? So what we did in this case was looked at different input possibilities. I'll just play this and I'll stop it for a second. Are you going? Play. No, yeah, that's it. We'll stop it in a second. So I think this was a super cool idea. So these experiments were all done under lockdown, so we couldn't go and do these things in real situations. So what we did is we got some 3D models of trains and planes and all those kind of objects. We got Romain, a student. We sat her in the green screen, and then we composited her into the 3D world, so that she could do interactions. And we have some avatars in there, but we also have the real Romain. So we did lots of different types of inputs and lots of different situations. So we went through all the different things we could think of that you might do as inputs. Inputs on your body, inputs in space, inputs on the seat in front of you, all sorts of things. I'll not go through them all, but you get the idea. We did it also in different forms of transport. Sometimes when, in this case, she's sat there next to somebody else, but we did it also with looking across at somebody and different types of transport scenarios. There you are, you can see some of the scenarios. The thing about that was then very strong effects of the environment on the types of input people felt comfortable doing. So for example, if you're sat on your own in a single seat, you would do different things than if you were sat opposite somebody without a table in the middle. For example, if you're on your own, people would be happy to do kind of foot tapping or tapping on the leg. But when they were sat opposite somebody else, it felt a bit weird to be kind of tapping on your leg or kind of like touching their foot. So the physical environment made a big difference on the kinds of inputs, as well as the outputs, as on the inputs as well. So these face-to-face seating layouts affect acceptability and the different types of inputs. So people didn't really like, for example, those mid-air interactions that you might typically do with a VR headset. People didn't really like doing those when there was somebody sat opposite them. You could be punching them or waving in your device in their face. That's not really very acceptable. So lots of interesting questions come out of that. And it really provides some kind of constraints on the design space because with this technology you could do anything, but actually you can't. There's a lot of restrictions about what people would feel happy to do. So a few kind of questions come out of that. Some maybe more technical ones. I thought I'd focus on a few more of the engineering ones because we're at EICS. But hand tracking in confined spaces is quite difficult. So Quest has got quite good hand tracking, but as soon as you have your hands down like this in your lap and looking down, it doesn't work quite so well because the camera doesn't get quite such a good view and maybe it's in quite shadow. So hand tracking in confined spaces is not quite so easy as when you're doing interactions in front of you like this. I guess they didn't really optimize it for that. Surface tracking, if you want to do interaction on that seat back in front of you, that needs to be registered well with the physical object. The physical object of the seat and the virtual object need to be very well registered, because if they're not, it feels like you're pushing through the object or you're trying to touch it and it's not in the right place. So getting precise tracking of the surfaces is important as well. And then other people in the environment. So if I want my tools to kind of help me configure my displays, and I know that I don't want to put one in front of cleansed space because that would be really embarrassing, well, how does the system track where those are in the environment so that it can help me do those kind of layouts? Right now they don't really do anything like that. I might get passed through on my camera, but that's about all I get. So there's lots of things that we need to do, tracking and other things we need to do to support these kind of interactions. Which leads nicely on into sensing challenges. So a really key problem is maintaining this forward bearing in an IMU based headset. So when you're driving along, you really want to know what is the headset movement and what's the car movement. An IMU can't tell the difference, it's just movement. But that isn't very helpful if you're wanting to stabilize the view. Otherwise the car turns and your Microsoft Word window goes over here and then you can't see it anymore. In devices which might do inside-out tracking, which is becoming more common, then you get this problem that the optical says, well, I know what's going on, the environment's not changing, it's totally fine, and the inertial says, no, it's moving. And then the fusion of those starts to fall apart. So in the future, maybe the inside-out tracking might be a good solution, but right now, the sensor fusion is designed for you using it at home still. It's not designed for using it in motion. And another thing then is obtaining vehicle telemetry, so that the car knows what direction it's going, what speed it's going. It's very handy if you can use that to help disambiguate what head movements and car movements. And there's a standard for that, it's called ODB, but oftentimes cars only report that very slowly, not at the frequency you would need in order to be able to do good tracking. So what we built, and I'll talk a bit more about, is this low latency sensing platform. You can see some bits of it there stuck on the car dashboard. We saw that in the video earlier on, which is us trying to separate out head motion and car motion. So one thing we spent quite a lot of time doing is driving around people in the back with headsets on to try and work out what headsets actually work in cars. So these ones I mentioned, well, they all have IMUs, it's just some only have IMUs and some do inside out, so they have optical tracking as well. And that often fails. So we did lots of driving around Glasgow with people wearing different headsets to try and find out which ones were robust and which ones weren't. Because unfortunately, in pretty much every headset, that's totally black box. You can't get inside that. Oftentimes, it's optimized to death by the manufacturers to try and reduce latency as much as possible. So you can't get in there and say what's going on. So we did a lot of driving around. Quest 2, if anyone's familiar with the Quest 2, it's terrible. Don't use it in the car. Vive Focus 3, no good. Pico Neo, the Pico ones actually seem to be the best so far. They drift the least, so they're the ones we're now starting to use. We had used Quest quite a lot, but as soon as you come to use that in a car, it just goes crazy because it gets confused. So there's a lot of issues with sensing around what happens inside the headset in order to optimize its performance. And they're just not designed for use in these kind of scenarios as yet. So here's our setup. So we just used off-the-shelf components, mostly SparkFun components. But so this is kind of a low-cost platform. These are just things you can just can buy from your hobbyist store. So then we can do our own alignment, have a separate IMU in the car to do our own alignment, drift compensation, so that we can then know what the car's doing and what the head is doing, and then we can subtract one from the other so that we can then stabilize the view, for example. So we made a Unity plugin for it, and this is now open source. The idea is that we've made this passenger motion platform to help us and other people be able to do research in cars to solve some of these kind of really annoying underlying problems that stop you doing what you want to do. I'll show you a little video of it in action. So you can see the black box underneath is just an old box of something which we taped them to. That isn't a key part of the whole technology. And the nice thing is, the headset, the device broadcasts the data to all the headsets in the car, so you can have multiple people doing similar things or different things, and you can configure it all nicely through a Unity plugin. And it tries to go low enough latency, because what you don't want to do is introduce latency, because that's going to lead to motion sickness. So a lot of the work in headsets has been reducing latency to try and avoid motion sickness. So we don't want to bring it back in again. You get the idea of some of these. We've seen these videos before. It's just to show now that sensing platform works in real time to allow us to, in this case, not stabilize the view. This time we're taking car turns and using them as part of the game. If you're familiar with a system called Holoride, which kind of spun out from Audi, they do a similar kind of thing for this, for Audi cars. Sadly, theirs one is not open source. And then we can detect the movement of the car and detect the movement of the head, and then stabilize the view. This would be you working on your Word document, or you watching the movie in the car. You need to stabilize that view. You can see we drive around and round and round this piece of kind of green area just in front of our department. We do a lot of driving around and around that little space. So you get the idea. So the thing is, this is low cost, off-the-shelf components. We've open sourced the design so that anybody can use that to give them a platform to start developing applications for the car and not have to worry about all this kind of sensing stuff that goes on. So we've seen the shared experience one before. So lots of questions to do with sensing. The headsets themselves don't really do a good job when on the move. They're not really designed to be used on the move. Sensor latency, particularly getting information from the car. This ODB in the car does not update very quickly on some cars, so you end up with latency, and latency causes motion sickness. We need to do something about that. Now, we know that cars have got all this stuff integrated in them because they're using it for their own navigation systems, but many, or let's say all, don't export that, so there's no way for us to get it. If you use your HoloRide system in an Audi, then we believe the Audi entertainment system does give some of that out, but it's not open source. So that's why we had to make our own version of that. But there's no reason why you couldn't do without our platform if the car just broadcast all that data that we know it's collecting. But at the moment, that's all proprietary. Yeah, I mentioned this before. The other thing that we do a lot of, as you saw it in several of those there, is kind of simulating AR, but in VR. So when you saw the Mark using the Word document there, behind him there was a kind of model world. It wasn't the real world, it was just a model world. So we do quite a lot of that work in VR because the AI headset's just not up to it yet. You can't create that level of experience that you can with a VR headset in AR. So we end up doing a lot of simulations. So I think we're waiting for the AR headsets to catch up with where we really want to be, and they're not there yet. All right, let's think a little bit about the last thing. So all those great experiences and interactions and stuff that I just talked about, there's one problem behind all of those, and that is motion sickness. If you don't solve the problem of motion sickness, it's hard to do all these interesting things you want to do as passengers. Now, of course, many people suffer from motion sickness, and that happens right now. If you're reading, you're looking at a book, your eyes are looking at the book and it's still, but your vestibular system is picking up the movements of the car, and that mismatch between the visual and vestibular is the current model of why motion sickness occurs. So many people get sick. My youngest daughter gets sick. She can't do that. She can't do that stuff in the car. It happens to people on phones, on tablets. In the scenario where you have the cocktail party in your car where the front seats rotate and you can talk to the people in the back, that's really likely to cause motion sickness. Many people will get sick when they're traveling backwards. I don't know about any of you, but many people don't like going backwards on the train even because it can cause motion sickness. And that kind of motion sickness means you can't use the travel time in a nice way. Maybe you have to spend the whole time looking out the window at the horizon trying not to feel sick. That's not really much fun. And immersive content makes that worse. If you can't see any of the outside world, you can't see out the windows to get any idea at all of the real world movements, that's likely to cause even more motion sickness. And this kind of headlock content that we talked about before, it's the most useful because I want to watch a movie or play a game and I want it stabilized in front of me. But that causes the mismatch. My eyes are still, but the car's turning and my head is detecting all that motion. So that condition that we really want, this exocentric headlock content, that's what causes the most motion sickness. So if we can't solve some of these problems, then we can't really do any of those things I showed you on the previous slides. So having not really thought about motion sickness at all in any of the previous time of my career, now motion sickness has become a huge topic, much bigger than I thought it would be. So yeah, how can we reduce motion sickness so that we can use these immersive displays in cars? Now this might not even be VR and AR headsets. You commonly see concept cars where the windows become screens on the insides. Great, I've got all that wasted space, let's make it a screen. But now I can't see outside anymore. That's going to cause motion sickness. But even for reading a book or playing a game right now, if you could reduce the motion sickness, that would be a benefit right now, let alone in the future when you might be using VR and AR headsets. So, of course, there are two parts. First of all, you need to detect when it starts. If people don't have motion sickness, great, then there's nothing you need to do. If they do, and you can detect it started, then if you can mitigate it early, then you might stop it happening or stop it getting to a level where people feel really bad. So there's kind of two parts to the problem. So we finished the first part and got some good results there, and we're now in the middle of the second part. So motion sickness detection. There's been some work on this in the past about trying to work out when it starts and detecting it. There's some physiological measures and things like that, but we started doing it through EEG, and then looking at various physiological sensors that we could use that might correlate with an EEG signal, so that we had something a bit more convenient. You don't really want to be wearing an EEG cap in the car, but if you could wear some other kind of sensor that was less intrusive, then that might be more useful. So we built this setup. You can see Gang there, who's the experimenter who works on this in the setup. So we're measuring EEG, and then we measure a few other physiological signals as well, particularly things like fingertip temperature, heart rate, facial temperature, a few other things like that. So we built this little bit of software which will allow us to detect and record all of that. We give people different types of environments. The idea is we're only inducing moderate motion sickness. We were very clear on that to the ethics committee. We do not want people to throw up in the lab, although we have had a couple of cases of that. So moderate motion sickness rather than really heavy motion sickness. So we only recruited people who weren't too motion sick. When we gave them different types of stimuli. The first one was just an attention task, where you just have to follow this thing moving around on the screen. Then we moved up to a tunnel task. If you could think about that, it's like a tunnel, and you're kind of flowing through this tunnel in VR. So there's more motions going on. And then the final stage is a VR roller coaster. Gang calls this a kind of spicy stimulus. So you're using a VR roller coaster. You've probably tried one of those, where the roller coaster is doing all sorts of crazy things, and you start to get motion sickness from that. Now, some of this, of course, is simulator sickness because they're not in motion. And some of it is motion sickness because we also do this work on a rotating chair. So there's many similarities between simulator sickness and motion sickness. So looking at one is probably helpful for the other. So we started with people static, and now we're testing them on a rotating chair. So we can do that rotational aspects. We're going to move on to the full driving experience a little bit later in the summer. Unfortunately, we don't have a very expensive track in the university where you can drive along, but we have got a rotating chair, so it means we can do some parts. But there's no reason to believe that the rotations are different to the lateral movements. They're really the same. So we found that the brain frontoparietal connectivity decreases with an increase in sickness ratings. Don't ask me any hard questions about that, because I'm not the EEG expert. I work with people who are. So we found that there was an effect that you could see in the brain from EEG. So then what we wanted to do was find some physiological markers that correlated with that, so that we had something more feasible to use in the car. So, for example, we looked at heart rate, fingertip temperature. What you can see on there is FMS is fast motion sickness score. That's the top scale. That's just a way that people rate motion sickness during the experiment, so we can kind of have a real-time measure of their subjective motion sickness. Got heart rate there. We've got fingertip temperature, and then that's the EEG results at the bottom. So what we found was, we can find a location. So we can see in the brain that there is an effect for motion sickness, which gives us an area of the brain to focus on, and we can see that there are these physiological markers that we can measure, which is actually really useful to have in the car. So fingertip temperature turns out to be a really good model. Pupil size turns out to be a really good model, and actually that's quite nice because many headsets these days have got eye trackers built in, so you kind of get that for free. So once you can detect it, then we can think, okay, right, what are we going to do about it? So how can we reduce the motion sickness? So we've got two solutions to this. The first one is neurostimulation. So we saw some effects on the EEG, so we have some ideas about which bits of the brain we might want to do something to. And then we have some visual displays. So the nice thing about, for example, a VR headset is we can control every pixel that you see. So that means we can turn that to our advantage and use that to help deliver some cues. So here is, this is the EEG. This is the experiment going on, you'll see. So this is the rotating chair I mentioned. So we have people going through this tunnel task. As the tunnel rotates, the chair rotates, so we can generate motion sickness. And then we've been looking, for example, at neurostimulation, transcutaneous alternating current stimulation. Maybe I'll play that again. So TACS in a particular area of the brain means that the fusing of kind of vestibular signals and visual signals maybe get slightly confused, and then your brain will use one of them and not the other, in which case it might use visual and not the vestibular, in which case then you're fine, because then there's no mismatch. We've done that in the lab quite a lot. Before we show any more of that one, we've done that in the lab quite a lot, and actually that works pretty well. I'll talk about some more of those results in a minute. So yeah, neurostimulation. The next part of the neurostimulation study is looking at vestibular stimulation. So there's a company we're working with called Otolith, who make a device which vibrates on these mastoid bones just behind your ear. A bit like bone conductance headphones, but it's not sound. And they claim there again that adds some noise to that vestibular system, and the brain thinks, yeah, the vestibular system's not working so well, we'll just use the visual, and then the mismatch between the two goes away. So that's the next part of the neurostimulation study that's ongoing right now. So that's the neurostimulation side. You might say, well, that's a little bit of a harder sell. Do people want to have their brains stimulated in the car? Depends how bad your motion sickness is, I suppose. Maybe an alternative solution would be, yeah, well, let's use some pixels. We've got all the pixels under our control. How might we use those? So we looked at this idea of a peripheral visual display. So I can show Alex driving around in the car again. So what we've got here is on the right, you can see, top right, you can see Alex being driven around in the car wearing his headset. Bottom right is the streets of Glasgow that he's been driven around in. And on the left, it's what we call this peripheral visual display. So here, this is a virtual world mapped to the movements of the headset, and therefore the movements of the car. Mapped with very low latency. So if you do that, no motion sickness. The visual display matches your vestibular. As long as the latency is low, that's fine. Nobody gets sick with that. That's not very useful, because that's a particularly boring landscape he's driving through. The idea is that what you would see, it's a little hard to see in the video, but you can see it around the edges on the middle there. The idea is that you'll see that just in your periphery, same as if you were just seeing the world going by out the windows in the car. So he's looking at the video in the middle, but he's seeing that peripheral visual display at the sides. And that maybe, that's just enough so that he can see what's happening in the real world, but also still attend to the video. Because the whole point of this is looking at the video. You don't want to have no video, because then there's no point in using the VR headset. And actually what you can see him doing there, he's doing that motion sickness scale as we're going along. So he's filling in that motion sickness scale so we can get an idea of his current motion sickness level. And in all these studies, we have a cutoff well before the person should get sick, so that we can stop the experiment if anybody starts to feel bad, so that we're not making people puke up in the car. The other part is maybe giving your visual system a little tweak to see if that would be enough. So what we can see here is, again, a student in the car, in the rotating chair. So here we have a display. It's got some maths questions in it. That's the task we get them to do. And that display, as the chair turns, the display just turns a little bit. Not the full distance. So if you turn 90 degrees, you'd be looking at the edge of the display, which would not be very useful. So actually what we have in this case is a rotation of 0.3 on the display compared to the seat rotation. So it just rotates a little bit. The idea is that small rotation helps synchronize your visual and vestibular. I'll just play it so you can see. It's a little bit hard to see from the video, but that area in the middle with the maths questions just rotates slightly as you rotate. So as it turns out, yeah, that does give you enough to reduce the feelings of motion sickness. So it helps your visual system just know what's going on, but without making the display unreadable, because it would be too far to the side. So neurostimulation experiments are going on. The TACS ones, which is the neurostimulation transcranial alternating current stimulation, was pretty successful. So people got significantly less sick from that. We're doing stimulation behind the ears, the vibration behind the ears, that's ongoing. The idea potentially you can even combine both of those two. The peripheral cues, the ones with the motion world just behind, that reduce motion sickness for some people, not all, but that helps some. And the one where you change the rotation slightly, that significantly reduced motion sickness for the people who took part in our experiment. So we're starting to get some results here to say, yeah, actually, we can do something about motion sickness. I wouldn't like to say we've solved it yet, but we're on the way. We're looking at also how you might use other modalities. So people have shown that maybe you could use audio. You've got a 3D audio space in the car. Maybe I can use some of that to cue the things that are happening. Or maybe haptics in the seat could maybe do something. So those are studies we're hopefully going to start soon. So then the whole thing here really, we're trying to create this kind of closed loop system where we detect the motion sickness onset. If you start to feel motion sickness, we apply some gentle mitigation. If it gets worse, we apply a bit more. We keep applying it. Maybe it starts to go down again, then we can stop applying it so that we can kind of manage the level of motion sickness that you feel down to 0 or down to a manageable level. Maybe we can never do that for everybody, but there might be a large proportion of people that we could actually get rid of that. And then you can start to use all those fun applications I showed before. Without the motion sickness control, it's hard to do that. So right, better have some conclusions. So yeah, as I said, we spend a lot of time as passengers. In Europe anyway, we spend 12,000 kilometers a year on average, which is a lot of distance and time. So can we use that in a more interesting way? And we're likely to become passengers more in the future of autonomous vehicles because nobody will be driving. The vehicle will be driving itself. So that's going to increase the amount of passenger time. So can we use it more effectively? Can we do something interesting with it? Rather than just being on our phones, could we do something else? As I said, our main focus is entertainment, work and collaboration. So I can have a big cinema screen in front of me and I can share that with my friends, or I can be playing games with my friends, or I can be working on a large multi-monitor setup like I have in my office. But I can do that on my flight somewhere. But there are a lot of challenges going on in the background. We're starting to try and work on some of these, but there's huge problems still for us all to work on, I think. I think it's a really rich area. So interaction in confined spaces. Nobody really in HCI has thought much about confined space. It's not really been a problem we've ever needed to think about. But for traveling, it's really important. I've got a seatbelt on, I'm strapped in, I've got a small space. How do I interact in that situation? The fact that I'm doing that in public also has interesting constraints because there's things I can and can't do in public. There's a whole load of sensing difficulties, trying to sense the person's hands in that space, trying to sense head movements versus vehicle movements. And then there's this big issue of motion sickness. If we can't do something about motion sickness, then we can't really enable those applications that we want. So our real aim here is to try and unlock this potential of travel time. So it's not just boring, wasted time anymore. We can unlock it so we can do fun stuff and do fun stuff in our future vehicles. Being a traveller and being a passenger is about to change because of autonomous vehicles. So how can HCI take advantage of that and do something useful and fun with it? And with that, I will finish.
Thank you very much. We have time for questions. Steve? Otherwise I can start maybe. When I was a kid, my sister was always sick in the car and there were several devices available. I don't know if you remember there was something at the queue of the car.
Oh yeah, you can lay on, that went on the ground.
Yeah, exactly. So is it completely not true? Or
I think that was completely not true. You can get wristbands which have like a little thing that goes into your... Yeah. I think, of course, you can get medication, and the medication does work. Okay. But then if you're too drowsy to enjoy yourself, well, that's not really the point. So yes, there are solutions right now, but they're not really great solutions for work or play or anything.
And then the second question related to that, do you have a level of, you say people are more sick or less sick, or do you have a level from 1 to 10, or can we rank everybody there, or do you have this?
So there exist already lots of scales for motion sickness. Okay. FMS, this fast motion sickness, SSQ, another one. There's a whole load of different scales out there that people have used to measure motion sickness in the past. So we're not inventing our own ones, we're just reusing existing ones for our studies because they're well validated.
So you do a test with somebody and you say your scale 3 and then you can use that?
Yeah, so we use that, for example, as a screening mechanism before they can take part in our experiments, because we don't really want to make our participants sick. We want to make them feel a little bit sick, but not actually be sick. So yeah, we really carefully screen people before we start, just to try and avoid that. Well, like I said, we did have two cases.
Thank you. Yeah, plenty of questions, so I will do all of them.
Have you done any preliminary studies with augmented reality headsets? Real ones?
Yeah, so we've done, we're doing a HoloLens one right now, so I haven't really got any results I can talk about. We did a previous one, I may have a slide. Did I have a slide on that? Where we were looking at, for gameplay, playing games in the car. So what we did in that case was, this is using Nreal, if you're familiar with Nreal. So what we were doing there was using the external world of the car for gameplay. So in this case, zombies are coming towards you. And if you can see this little guy, there's a little guy, can you see my cursor? Oh no, you can't see it. Just there. There's a zombie coming towards you. You have to shoot them. And the cars in the real world give you health or ammo. So you can see a couple of cars. So we detect the cars in the real world and then randomly augment some of them with bullets or with health. So you can use to shoot them. And then, as it gets closer, eventually the zombie gets you, and then your windscreen starts to crack as the guy comes and attacks you. So there, we were trying to use, we did that driving in a car, so trying to do something augmented, so that we took some aspect of the real world and used it for gameplay.
Less motion sickness?
So in that case, not so much motion sickness, because the virtual is very small compared to the real. So if you've only got a few pixels worth of virtual, yeah, you're fine. But the more you move towards the fully immersive, the more likely it is to cause motion sickness. So in this one, nothing really, because you can see you've got some kind of highlights on those vehicles, but it's not really occluding your view.
Thank you.
But that was a really fun game as well.
I have the next one. So basically, I have two questions. One is, I also have motion sickness very often when I'm in a car and reading books, something like that. But I do not have that in a train, because the trains nowadays, at least in Germany, they do something like this if they drive the curve. Did you also try out whether it's also possible to change the orientation of what you see more or less via this axis? It depends a bit how you name the axis.
So we haven't done that. We've done this axis, as I showed in one of the later slides. So there's no reason you couldn't do that in any axis you like. So because we're in a rotating chair, we're only doing this. So that's why we use this one. But yeah, you could do it in different axes. Now it's interesting that you say that doesn't cause motion sickness for you, because I've talked to a lot of people. So in the UK, we have quite a lot of these Pendolino trains where they rotate into the corners, and some people get really sick from that.
Okay.
So if something like that, maybe compensating for that with this axis might be really good for them.
Yeah. And another question. You said that there are maybe interactions that you do which are socially not acceptable currently, but I see more and more people walking around with these small earbuds and they are continuously talking. You always ask yourself whom are you talking to?
Yeah.
I think in some months or years it's going to be fully accepted. Do you think that there may also be a shift?
Yeah, I know that's a great topic. Actually, we were talking about it on our table at dinner last night as well. So yes, we started doing social acceptability work quite a long time ago. If any of you know Julie Williamson from Glasgow, that was her PhD topic, and that was kind of in the time almost when that Bluetooth headsets were new and people were doing gestures on phones in the street, and some of that has become acceptable. So yes, some of it might change, but in some ways you've got to get over that first barrier. So you've got to pick things which are more likely to be acceptable to start, at least, because if you pick some crazy gesture, okay, you've got to do this to start. that's just the wrong choice. So at least you can say, well, okay, these ones maybe we should leave till a bit later. Let's try with these ones because they're more acceptable. And of course, as I said, it depends on the environment you're in. If you were on the single seat on the train, then you were much more flexible about the things you can do than if you were the one where you're looking at the guy right opposite you, and people felt very weird about doing those kind of things. So maybe some of those would never become acceptable because it's always going to be weird waving something in someone else's face, or even just like looking at them in their eyes when you're in your headset, but they don't know what you're doing and looking towards you. So some of those things may never go away.
Jürgen?
Thanks for presenting this really interesting work. I understood that one of your guiding questions is, can we use time more effectively? This is probably true for repetitive travel, but there are many other situations where one could also ask, how can we make travel more interesting and more engaging? So, for instance, when traveling here along the Côte d'Azur, driving, but could as well be when being driven by an automatic car. I would like to know, what is this interesting building here? Did any movie stars stay there? Did any stories happen there? And so on. These data may be hard to get by, but I was wondering whether you're also looking at situations where you're not detaching people from the outside world, but where you're actually immersing people more strongly in the external environment.
That is a great topic. So the video of me and Katrina on the bus is a little bit like that. So we were driving past the model of Glasgow station, and on the side of that was augmentative information about the station. You probably can't see it in the video very well. So in this case, it was just a model, but the idea exactly that would be a tour bus, a virtual tour bus kind of thing. So you could be, see that stuff is augmented on the side of the model of the station, could be augmented on the side of the real station. So yeah, I think that exactly talks to the kind of thing you're saying there. We really would like to do that as well. So that tour bus scenario is one we think is a good one. And of course, you could be in the tour bus with me, even though you're in Nice and I'm driving somewhere else. You know, then we could be sharing that experience. One is virtual, one is real.
Cameron, this question?
Yeah. So I'm just curious. Do you have some data on, how willing people actually are using this kind of thing in real life?
So yeah, we collected some of that from the social acceptability studies I've talked about. So we have data about that. The one thing we haven't done so much of yet is put people really in those settings wearing headsets, because we started this project during lockdown and we just weren't allowed to do that. So that's something that we are aiming to do. Well, actually, we were going to do a study on the way to Kai this year with people on the plane, because there was a bunch of Glasgow people going, and we thought, well, we'll share out some headsets and do it. We just couldn't make it work in time. We just didn't have time. But yes, so we have people looking at virtual scenes. And for example, from Julie's work in the past, we found that was a very good predictor of what they would do when they were really on the street. But I haven't done that last step yet for this one, where we've really looked at people using VR in public transport. So over the summer, we've got Laura, one of the students, is going to do some work with VR headsets in public transport, and her topic of her PhD is social acceptance. So she's going to look exactly at that. And then we've got other plans to do things in cars and other forms of shared transport a little bit later. So we're going to get there, but we've not actually done those real studies yet. That's lockdown's fault.
Oh, great, thanks.
And the last question from Nadir.
I wonder, you were talking about how big or how small the augmented reality display is, and the fact that it doesn't actually create any motion sickness because it's so small. So, two interrelated questions. Do you know what is the biggest that you can get in order not to have that? And if you do, but if maybe you don't, is it feasible? Did you try to actually use real cameras looking around you, maybe the actual camera, to recreate this kind of frame around instead of creating like a virtual world that kind of moves like you're moving? Instead, you're actually looking out, and you have cameras that looks who is on your side, who is on the other side, who is in the front, and kind of this frame around your main view is the actual real work. This could also help with this problem of knowing what's happening around you and increasing the awareness.
Yeah, I mean, I think if you had a really good AR headset, you'd get that for free, because you could just see all around the real world anyway. So we haven't done that particularly, but I think if you wore an AR headset, you wouldn't have to worry about that, because you'd just be seeing it. The first part, we haven't. I can't tell you what size is too big or what size is too small. It would totally depend on your resistance to motion sickness, I think. But you know that if there's none, that's perfect, and if it's fully occluded, then that's most likely to cause problems. So there's that virtual reality continuum. It's exactly there. Where the sweet spot for you might be different for me.
You might be able to measure it and do it, personalized to some extent. But my first question was more about VR. Why don't we do that with VR as well? You use actual work instead of a simulated work around the frame.
So there's a nice tool that works on the Quest, which we were going to use whilst traveling. I can't remember what it's called, but it lets you draw portholes. You can draw a porthole and it shows the pass-through camera view, a real world view, in that porthole in the middle of your virtual scene. So you can do that. We wanted to do that for travelers, but of course the Quest 2 is shit in transport. It just goes crazy. So you couldn't do it. But if you could do that on public transport, we would be able to do that experiment right now, because you could just draw a porthole and it shows the pass-through camera view.
Cool. Thank you.
Okay. Thank you very much. Thank you, Steve, for the answering questions.
Thank you for inviting me.
Marco has prepared something for you. So.
Yeah, I would like to thank you for your kindness and your thoughts.
Thank you very much.
All gifted to you.
Thank you very much, Marco.
It's a pleasure to have you here, and now that you're traveling back, you can enjoy all this technology you are producing. So thanks a lot.
Thank you very much.
Thank you very much again.
And I would like to thank you for this edition of EICS, and looking forward to see you next year.
Yeah. Thank you, Marco. And now I call Jose Camps, the chair of the steering committee of EICS, for saying the last few words before we close the conference.
I hope you enjoyed EICS'2022, but before I do the introduction of next year's, I would like to thank all the involved in organizing this edition, all the organizing committee, the reviewers. Also, thank you for being here, and in particular, I would like to thank Marco for chairing the conference, and we also have something for you.
Oh, thanks a lot.
You can at the bottom of the slide.
Okay. Wow! Muito obrigado. This is thank you in Portuguese, so thanks a lot. Oh, great. It's a veuve clicquot rosé, like the good wine. Thank you very much.
Thank you. And so now that 2022 is finishing, or EICS'2022, so we can start thinking about next year. We are closer to the sea. We will continue to be closer to the sea, maybe even a bit closer to the sea, because in 2023 we will be going to Wales, to Swansea, and EICS'2023, the 5th edition of the conference, will be organized by Alan Dix in the Computational Foundry, which you have some pictures there. It's by the beach. Alan couldn't be here, but he sent us a message which I will hopefully now play.
Hi
Yes?
there. I'm Alex, and first, very, very sorry for not being with you today. I had a sort of family-related event this same week that was delayed for 2 years due to COVID, so I'm afraid I have to take precedence. However, I am really, really looking forward to welcoming you all to the EICS 2022 next year, which is going to be held in Swansea in June. So I'm hoping that many of you who joined this year will be with me and everybody else in Swansea next year. This is only the second time EICS will have been held in the UK, and it's the first time in Wales. So I'm especially looking forward to welcoming you to my homeland. So I'm going to say Groeso I Gymru, which is Welsh for welcome to Wales. Wales is a beautiful country, so I'm hoping you get plenty of time to visit beyond Swansea when you come next year. There's a glorious countryside, loads of heritage, lovely and special foods, and just lots and lots of friendly people who will make you very, very welcome. Swansea itself is situated at the edge of the Gower Peninsula, and this is one of the first designated, or it's the first designated area of outstanding natural beauty in the UK back in 1956. And both a beautiful area, but also one that's really important environmentally. However, Swansea was also at the heart of the Industrial Revolution. And back in the 19th century, it was known as Copperopolis, because the valleys behind Swansea were just full of copperworks. It was the centre of the world trade. And even today, Swansea sort of sits at the edge of two worlds. If you look one side out from the campus, you look towards the Gower Peninsula and all of the natural beauty there and all of the recreational aspects of that. If you look in the other direction, though, there's Tata Steelworks. And it reminds us that as we're developing these new technologies of the 21st century, the digital technologies driving us forward, we've got to look both to the sort of industries that have been developed from that, but also looking to create a sort of humane, sustainable world, to think about the well-being and general life as well as the economics of it. I hope that's something that we can capture in the conference next year. This picks up actually themes from Swansea University itself. So it recently celebrated its 100th anniversary, and the motto of the university is Gwegu Correct Idam, which means technical skills direct in our culture. Again, trying to bridge those worlds. I hope we'll capture some of that at the conference. EICS 2023 has been hosted in the computational foundry, and it's a £32.5 million investment that's by a joint between the Swansea University, the Welsh Government and the European Union. I would say that the ground underneath the computational foundry building is fully Welsh, but everything above that is paid for and definitely very solidly European. So I think a welcome place, both a very Welsh place, but a very European and global place to be. And the mission of the foundry is to nurture groundbreaking digital research that makes a difference in the real world. And I think that's something that I hope everybody at CSCS and community can grasp onto as well. We want to really use things that are at the cutting edge and yet make a difference. But as well as being a building and mission, the computational foundry is a community of researchers, and many of them will be helping make the EICS an experience that I hope you'll remember, both for its technical programme, but also for the human companionship that any conference, but particularly a tight-knit community like EICS brings. For me, I mean, this has been important. Again, it's a great pleasure to be chairing next year's conference. Many of you know my earliest work was in formal modelling, formal methods for interactive systems. And the various conferences that gave rise to EICS were my home in those years. Some of you remember the DSCIS series, EICS'2022, and those, yeah. And I was even at the, which isn't on the graph, the little picture, I hope we'll get it in for the next year's website, and the picture, the EICS history picture. There was the founding formal methods in computer graphics seminar, Eurographics seminar in 1991 in Pisa, which I think was a sort of precursor to the EICS series. I was very pleased to have been at that. The reason I was mentioning this is the Swansea also hosts a history of computing collection. So I'm hoping for the old hands of the EICS, perhaps this is the opportunity to pick up some of that history and the stories of how the conference developed. However, there's also, for those who are less old and less grey in the beard, know for many of you this is the case now. This is a community that is allowing you to grow and nurture, and again, I hope we can do that for you in EICS 2023 as well. I think I've said plenty about Swansea, I've said plenty about EICS 2023, and so the only thing that remains to say is Blwyddyn nesaf yn Abertawe next year in Swansea. Goodbye for now, and looking forward to seeing you.
And so, just as a final information, it's the schedule for submissions. So, as usual, now we will have 3 rounds of submissions. So, if you don't meet the July round, you can submit in October or in February 2023. Actually, sorry for that typo. And start thinking about the papers. And yeah, all the other dates will be on the website in time. Thank you.
See you.